After that, generate the echo signal. So in my paper, show the two simple results. First one is to the result in comparison, the simulation and the experiment. I mean, I will check our simulator quality. Another result is to check the effect of both the sensor configuration and ground conditions. So you can see here, so this is the visualization tool. There are one difference point, that is the emitting angle. So you can see here, the shape is different. So if you are interested in my research, so I'll be here. So please ask me. That's all. Thank you for attention.
Okay, thank you very much. You still 1 minute, so any questions? Please?
Yes? Yes. So I used this model, After Effects. This is a commercial software based on the LMAP. LMAP means this plant growth model developed by I'm not sure, French Institute. I used this model. This is the idea. So, yes, isolated tree. So next step,
Okay, thank you very much. Okay, so good. So would you like to move on to the next speaker? The next speaker is Dr. Ali Asghar Darveshov from Iran. His title is Investigating the Capability of IRS PU6 LISS4 satellite image for pistachio forest density mapping, case study of the northeast of Iran. Please.
Hello everybody, my name is Darvish from University of Tehran, Iran. You know, the pistachio nuts from Iran is very famous, but there are wildfire forest pistachio in Iran too, which is very important ecologically and economically for local people. Since providing some information for this valuable forest was very important, we are trying to investigate to define the capacity of IRS is 4 satellite image for pistachio forest density map. A study area covers about 500 hectares in northeast of Iran at the border of Turkmenistan, as you see here. Here there are only 2 stands, pistachio forest, but no dense. The forest density is less than 25%, but very, very important wild forest. To evaluate the capacity of this data, we have prepared an accurate ground truth with 34 plots, each 1 hectare, to field work. We defined the forest density in 5 classes, as you see here. qualitatively. The resulted inventory was used to produce ground truth map. We have used a subset of map-oriented level 1 GIS is raw data with tree bands and resolution of 10 meter. The geometry correction was performed with GCP method, and various table enhancements such as PCA and distance-based vegetation indices were also calculated to reduce the influence of soil background, because forest is very low dense. We have performed a common classification such as maximum likelihood, minimum distance, and fuzzy to analyze the image. The best spectral band we have defined using Bhattacharya distance-based training area. As I said, we have prepared our ground truths in 5 classes, but the primary result showed very interfacing, spectral interfacing. Therefore, we have mixed some classes from 5 classes to 3 classes, and then we perform repeated classification. For the assessment of accuracy, we have used our ground truths result. The kappa coefficient and overall accuracy with 5 classes were very low. Therefore, we merged some classes and repeated the classification with 3 classes. In this situation, we have better result, overall 70% and kappa 0.4. Conclusion, unfortunately, this approach, conventional classification method and IRS data is not suitable to provide forest density map. We suggest better digital image such as ultra cam imagery with high resolution and object-based classification method to detect individual trees and then providing forest density. Thank you for your attention.
Okay, we have one question. No? Okay, thank you very much. Now we move on to the next speaker, Dr. Mitsuru Nasu from Japan. The title is A Case Study of a Forest Carbon Stock Monitoring System for Red T Plus in Lao PDR. Please, Dr. Nasu.
Thank you very much, Mr. Chairman. My name is Mitsuru Nasu from Initial Survey Company in Japan. Since 2009, First Inventory and Planning Division of Department of Forestry of Lao Government and Asia Survey have been doing a cooperative study of a forest carbon stock monitoring system for RED Plus with the financial support of the Forest Agency of Japan. As you are familiar with, the RED Plus refers to effort and initiative for the reduction of greenhouse gas emissions through rigorously increasing forest carbon stocks based on reducing the deforestation and the forest degradation in developing countries. Main objectives of this study were to develop technology needed for establishing an integrated measuring, reporting, and verification system for RED Plus, and to accumulate the technical know-how how pilot study areas of national, subnational, and project levels RED Plus prior to the establishing actual MRV system. For this study, 2 pilot study areas of entire Rambaban and part of Kansai provinces were selected as a subnational level study areas, and in 3 provincial provinces, in this province, 3 districts were selected as project level study areas. national level areas is the entire Laos. These pilot study areas are covered mostly by steep mountains ranging from 200 meters to 2,300 meter altitude. And driving factors of deforestation, forest degradations are increase of slash and burn, significant shifting cultivation, dam and road construction, etc. The scope of the MRI in RED+ mechanism is broad and complex, and our study consists of 5 components, as shown in this figure. We use the Landsat, AROS, W2, and Prism, MODIS images, and aerial photos for the deforestation and analysis using remote sensing technology. This figure also shows various outcomes of the study as an image. In this paper, however, result of remote sensing technology and photogrammetry analysis are mainly discussed. One of the main important topics in our study is multi-temporal land use land cover mapping for the subnational RED+ using medium resolution satellite images such as Landsat. In this study, bearing in mind the land use categories required for estimating forest carbon stocks based on the land use models in IPCC guidelines, etc., the classification categories suited estimation of the carbon stock were established, and the various practical ideas based on the field surveys were applied for improving land use land carbon classification accuracy. For this accuracy analysis of the 2009 Landsat land cover maps based on the definition of forest in raw PDR were carried out by field checking, visual image interpretation of band-sharpened AROS images, and interpretation of a measurement of tree height using AROS Prism stereo image. The overall accuracy of the non-forest and non-forest classification was about 80 to 90%. Then the satellite image from 1993 and 2000 were also classified using this method. And also we found analyzed at district level land use and cover for 5 time periods to check the adequacy of the time intervals of the mapping. For forest biomass class, high, medium, and low were devised for evaluating the details of distribution change of the forest carbon stocks. Forest biomass classification based on the visual interpretation of AROS Abernir images was carried out on 2 kilometers about 18 point. So we use this for evaluating the carbon stocks. Estimation of the forest carbon stock was done for systems. Tier 1, Tier 1, 2, 1, Tier 2, 3, and Tier 3. And using the we use the forest carbon stock distribution model based on DBH and height of tree, and also tree height measurement using AROS stereo image and accuracy analysis of the dam. And the tree height versus biomass classes and carbon stock estimation was also established, and we developed this kind of system for this in this study. And as a summary, I think we developed level 1, level national, subnational, and project level MRV system and further study is expected for integrating project level and these levels MRV system. Thank you very much.
Thank you very much. I'd like to move on to the next speaker, Dr. Adam Steele from Australia. The title is Extreme Airborne LiDAR, Validating Air Survey over Antarctic Pack Ice. Please.
Thank you, Chairman. So this is just a one-slide number. So for the past 5 years, I guess, the Antarctic Division and ACIC have been flying an airborne LiDAR system over pack ice in East Antarctica in an effort to sort of validate satellite measurements of, or satellite estimates of sea ice thickness in the region. There's quite a large geophysical problem in that the volume of Antarctic sea ice that melts and forms every year is extremely poorly understood. So my research in this project has been essentially to validate a validation tool. And we have discovered we've got lots of interesting nuts to crack on the way. The first of which is that, you know, if it's pretty standard in LiDAR world, as you see from everyone else here, that you need a calibration, some sort of calibration target that you can use to make sure that your LiDAR slots match up and your angular, any angular offsets in your laser scanner and IMU system or navigation system are accounted for. But we have the interesting problem of a moving target, because while we can fly over a ship or some chunk of ice, it's constantly drifting. Nothing stays still in the pack ice. So that's been an interesting problem that we've had a couple of attempts to crack, including just modifying all of our aircraft trajectories so that we have a ship-centered coordinate system. But we're not quite there yet. If anyone has ideas, I'm not open to them. And our second sort of major problem is one that really requires application of money and time, but for various reasons the instruments that we're using are hard, basically bolted hard to an aircraft airframe. So here's our laser scanner and IMU system, but it's directly bolted to the helicopter airframe, which introduces a vibration problem whenever you start a helicopter and the blade starts spinning. So we can sort of determine what the vibration characteristics are, but as yet it's just contributing maybe an extra couple of decimeters to our LiDAR error. And I guess the last real big bugbear for us is that we only get to validate our data every few years. So what I've shown in these plots here is some aerial photography and LiDAR that we shot in 2007 with the set of instruments that are described up here. So that was basically our first iteration of this instrument package. And the only thing we've got really to validate the surface elevations we get from an airborne LiDAR are these set of drill hole estimates here, where we jump off the ship and start here and basically measure out a 200-metre line and drill holes through the ice, get a surface elevation above seawater. And those are shown in this red line here with a sort of approximate error bound of a few centimetres, just based on the fact that you can't really observe things that accurately in cold, wet places. And based on the 2007 data, which is the LiDAR flights, so what I've done is co-located drill holes and a region of maybe 30 centimetres of LiDAR points around each drill hole, and this black line represents the surface elevations we get from the laser scanner measurements. And they're in the same ballpark, and this big grey area is a fairly optimistic, I think, estimate of the error inherent in our LiDAR system. So, yeah, we've got this validation tool, and it's mostly valid, but as of 2007 and continuing forward, we've still got a fair chunk of work to be done on it. And fortunately for us, our next chance to do this is coming next month. So And I guess what we've learned from this is that well, the things we've taken away from this is that we've needed to update our equipment a little bit, get a better inertial navigation system with a dual frequency GPS system so that we can get a better aircraft trajectory. And we did put a better camera in the instrument because one of the alternative sources of validation that we've got are generating digital elevation models from overlapping aerial imagery. And I think that's where the future is headed for us. And that's it for me, so if you have questions.
Okay, thank you very much. You have one question? Okay, please. Sure.
How deep are your drill holes? Is this multi-year ice or first-year ice you're talking about?
It depends on where we can get the ship to. So this particular flight is just first-year ice. So the depths we're drilling here were probably actually around 60 centimetres up here, down to 1.2 metres around these little ridges that you can see there.
Okay, thank you very much. Okay. The Dr. Ferreira from Brazil, are you here? No. Dr. Wu from Taiwan? No. And then Dr. Ku from China? No. Okay. So we'll come to the Dr. Sulochana Shekhar from India. Her title is the Detecting Slums from QuickBird Data in Pune using an objective-oriented approach. Please.
Very good afternoon to everyone. I am Sulochana Shekhar from Central University of Karnataka, India. Today, first time in the history of mankind, urban dwellers outnumber the rural residents. The world is increasingly getting urbanized. Particularly the developing countries, they are undergoing urban explosion. When you say that in India, it is the same condition. In India also, by 2011 census, there are more than 300 million population is living in urban areas. So more than 30% of the people live in urban areas, and every 7th person in urban India is a slum dweller. So who is this slum dweller? What is slum? Let us see. Do we need to map slums? Yes. Why? Because they are part of urban population. They are supporting for urban economic activities. They are working for urban economic growth. So we cannot comfortably ignore them when doing the city development plan or city plan development or something. When you want overall sustainable development, we have to incorporate slum people also. Slums, when you talk about the urban expansion takes place either increase in population or aerial expansion. When urban increase takes place either by natural increase of population or by migration. So when the rural people from poor people, when they come into the cities, they develop the slums. So slums generally considered as an inhuman conditions where inadequate infrastructure, they are contiguous, more than 300 people living together within 60 to 70 hutments with a very congested environment like that. So when you start mapping these slums, why do we go for remote sensing? Compared to the traditional survey methods and other primary survey methods, remote sensing can give a fast and very reliable spatial data which we need for continuous monitoring the slum development programs, slum renewal programs, and to find out the suitable areas where the slums can be relocated. So in that conditions, we have to go for remote sensing. When you talk about remote sensing, urban remote sensing, there is always high spectral resolution versus high spatial resolution. But in some cases, high spatial resolution can score a better choice than the high spectral resolution. So here I have taken the QuickBird data, high spatial resolution data for mapping the slums of Pune city. Then again, why Pune? Pune is the third largest city in terms of slum population in India. More than 40% of the people live in slums or slum-like conditions. So Pune has been taken for this mapping of slums. The central scene of part of the Pune city, one QuickBird scene has been taken here. Here in that high spatial resolution, visually you can differentiate the slums as well as non-slums. But certain characteristics which can help us to incorporate or detect the slums from the image. So you can see here the high-rise structures with the